Oh Lord, we thank you for this day. We thank you for this great moment. Thank you for our lives. And Lord, we pray that you lead us when you're studying. You lead us so that we understand whatever you're going to study in this Zoom internet connection. We all don't know each other, but Lord, help us connect and understand whatever and each and everything you're going to study. In Jesus' name we pray. Amen.
Yes, amen. Now, best thing, when I asked last week, which section do you want to look at in light? According to the replies I got in my inbox, people were saying they need to look at refraction of light. That is what I got from my inbox, that people wanted to look at refraction of light. And that's where we are going to concentrate. But in case you have another suggestion, maybe after the lesson, you let us know such that we can buy your idea. But that's where we are going to concentrate for today's session. So allow me to share my screen. Hope my screen is on. Now, when it comes to light, we know very well that light has a number of subtopics that we can cover. I know in your schools, you have covered some parts of light. You have been able to cover the first part of light, and that part of light was about refraction of light at plane surfaces, where you looked at laws of refraction, types of refraction, you looked at deviation, plane mirrors, virtual images. That was the first part. Then after that part, you went on to the second part, which you can call chapter 2. And at that point, you looked at what you call refraction of light at curved surfaces. We have plane surfaces. Plane means something flat. Then from that one, you went on to curved surfaces, where you looked at curved mirrors, you looked at concave, parabolic, convex mirrors, you looked at how to derive, how to come up with those different formulas. So you came up with those things. So you looked at different examples, sine conventions, how to determine focal length. That was the second part. So that's what you call like chapter 2. Then the third part that we are going now to start on is going to be refraction of light. After refraction of light, if we finish that part of refraction of light, we can look at what we call refraction through lenses. And then the last chapter is what we call optical instruments. So those are the major parts we have when it comes to light. And the moment you understand all those parts, then it means that you are going to be able to do well in that section of light. So this is what we are going to look at. But before we start, I may need to have some idea what people think refraction is, or what you have heard about refraction. You can raise up your hand and you tell us what you think refraction is. Any idea? Refraction. Okay. So that is what we are going to look at. Now, when you look at my screen, you are not seeing some photos. Oh, I think I'm going to... You are not seeing some photos on my screen. And those photos are displaying the effect of what we call refraction of light. When you look at the first one, when you place a pencil in water, you can notice that the pencil will appear as if it is bent. That effect is what we call refraction. When you look into the swimming pool, always the swimming pools will appear to be shallow, yet they are already very, very deep. So that effect that we see, whereby things that look to be bending, is what we call refraction of light. There are two things, and do not confuse. We have refraction and refraction. So when we look at refraction, we are mainly concentrating at the bending of light. Whenever light is traveling from one medium to another, there is some kind of bending that it undergoes. That kind of bending that light undergoes is what we call refraction of light. So for an observer, someone looking at that object, it will always appear to be shallow, or it will appear to be bent. So that is the effect that we are going to look at in today's lesson. But as we dig deep into this section, what you need to know that when it comes to refraction of light, one of the things you need to take note that here we look at what we call mediums, or what we call a medium. In light, what we call a medium is like can I call it like a surface through which light travels? Light can travel through air, light can travel through glass, light can travel through water, light can travel through any medium. So these are the common mediums that we are going to be meeting. Whenever light is moving from one medium to another, it's what we call refraction. When light is in one medium, that one it can be called the refraction. But when light is if light changes direction in one medium, that's what we call refraction. But if light is traveling from one medium to another, then that kind of concept is what we call refraction of light. So refraction of light, the key things you need to know that one, light is going to change its direction. The speed at which you are moving is going to change. I can give you an example. When you are in air, when they tell you to run around a field, you know that you can run very, very fast and you find yourself finishing the race within 1 hour. But if they tell you to run in water, you're going to find yourself that, right, you can run, but your speed is going to be slow. You're going to be very slow when you are running. Why? Because the medium through which you are running, it is dense. So you are able, so that kind of effect is what we are going to be referring in as refraction. So now that same concept or that same analogy applies when it comes to light. When light is traveling in air being a less dense medium, light travels very fast. But when it enters into a medium that is dense, a medium whose refractive index is big, light tends to slow down. You slow down, like even you, when you are walking into water, you'll always slow down. But when you are out of water, you'll always move very, very fast. Now, that kind of effect is what we shall be calling refraction of light. Okay, now I'm going to continue. Okay, now what is refraction of light? When we talk about refraction of light, refraction means the bending of light as it travels from one medium to another of different optical densities. Now, when you are defining, these are the keywords. One, there must be bending of light. Light must be traveling from one medium onto another, and those medium where light is traveling should be of different optical densities. An example, I've showed you that if this is air and this is maybe water, or let me say this is glass, when light is traveling through air, here light will travel very fast because air is a less dense medium and glass is a dense what? A dense medium. So the speed at which it travels in air is always different when it comes to the speed at which it travels when it is in glass. So now that difference in the speed gives us what we call refraction of light. So when we talk about refraction of light, we are looking at the way at which the speed of light changes when light is moving from one medium to another of different optical densities. Let me hope we are fine on that. So there are two ways you can define it. You can define it in terms of speed of light, or you can define it in terms of the bending of light. But when you are defining, please take note of the keywords that when you are defining in terms of speed, at times even you can use velocity. It is no problem. The change in the speed of light as it travels from one medium to another of different optical densities. When we talk about densities, I want you can use water and you can use cooking oil at home. When you look at those two things, when you look at their densities is you are comparing the mass and the volume. When you are comparing the mass and volume of cooking oil and water, or you can compare any oil and water, you will notice that their densities are different. So that difference in the densities is what we call is what we are referring to as optical densities. So densities here, you are relating to the mass and you are relating to the volume. Let me know whether we are fine. You can send a chat that we can proceed, or you have a question. Are we good to proceed? Are people writing or? Okay. Okay, good. Okay, now we can, so when you check, they can ask you what is meant by the term refraction, and always they give it 1 mark. So when you check those question banks, like in 2011, you'll find that they can ask you to define what is refraction of light. Okay, we can proceed. Now, we need to ask ourselves, what causes the refraction of light? What causes refraction of light? Now, when it comes to the causes, take an example. Here, we can relate it. What causes malaria? In case I'm posing it in terms of disease, you'll find that what causes malaria is because one, maybe negligence to sleep under mosquito nets. Some people are just lazy, they don't want to sleep under mosquito nets. So that one can be the cause. Now we're asking, what leads to the change in the direction of light? What leads to that change in the speed of light? Now, what brings about the changes in the speed of light? What brings about it is because of the different optical densities. So refraction of light is caused because of the different optical densities. Light is always refracted differently in each of the mediums. When light is moving in a less dense medium, light will travel very fast. When light is moving in a denser medium, light is always going to travel at a very slow pace. Now, because the less dense medium have a small refractive index, they have a small refractive index. It means that light can be able to travel very fast. However, when it comes to denser medium, they have a large refractive index. When we talk about the refractive index, take an example. I have air, I have water. So when it comes to air, the refractive index of air is 1. When it comes to water, the refractive index is 1.5. Therefore, because it is moving from two different mediums whose densities are different, then it means that light is going to move, is going to change the direction. The same thing happens to you. When you are running in air, you run very fast. When you run into water, you are going to run very slow. Why? Because of the difference in the densities of the medium. That water has a bigger density than air. Because when you look at air, you'll find that in air, the refractive index is 1. When it comes to water, the refractive index is 1.33. So meaning that water is denser than air. So you cannot run very fast in water the way you can do it when you are in air. So that change, that difference in optical densities is what brings about what you call refraction of light. So because there is difference in the densities, it means that also the speed is going to differ when light is moving from one medium to another. So they can even ask you, what causes refraction of light? So here the keywords you need to mention is that it's caused by the difference in the optical densities. Yes, and now you can ask yourself, because also you are going to know, later on I'm going to inform you that when it comes to that refraction still, you are going to find out that that one, the speed and the wavelength also changes. So that's what I wanted you to know about it. We can continue. Now you can look at this. when you look at this figure, you can notice two things. One, we have this is A and this is B. When you look at figure A, this is air. Air is a less dense medium. Glass is a dense medium. Why? Air, its refractive index is 1. Glass, its refractive index is 1.5. So what happens is that when light is moving from a less dense medium into a denser medium, here you'll find that the angle is maybe 60 degrees. But because it is going into a denser medium, always light will bend towards the normal. This line here, the dotted one, is what we call the normal line. So whenever it is moving into a medium that is dense, the angle becomes very small. If here it was 60, here you're going to find that the angle is small. So it can be maybe 30, it can be 20, but it can't be bigger than 60 because now light is moving into a medium that is very, very dense. However, when it is moving from a medium, let me say here, where it's moving from water or from glass, which is 1.5, and is entering into air, and is entering into air, which is 1. Here, the medium is very dense and is entering into a small dense place. So in case here the angle is 30, you'll find that once it enters into a medium that has a small refractive index, the angle is going to be very big. So you'll find maybe it is 60 something or 70, but the angle will always be bigger than the other medium. Because here now, like its speed is going to be very big. Here, it will move at a very slow pace, slow speed. But the moment it enters into this medium that is less dense, light is going to move very fast. So it's going to have a higher speed. And when the speed is high, it means that light will have a very big angle of refraction. So when light is moving from dense to less dense, always the angle or the refraction is bends away from the normal. When it is moving from a less to a denser, always light will always bend towards the normal. So those two things you must take note of them. Okay. And when they ask you, briefly explain what causes refraction of light, you can state your answer in that format, that when light travels from one medium to another of different optical distance, its wavelength will change. So this is one of the causes. Then the change in the wavelength causes the speed of light to change, hence the direction might change if the instant at an angle which is not equal to 90 degrees. So basically there are two reasons what brings about the changes in the direction that light takes. So what makes the direction of light to change? One, it depends on the wavelength. And the second one, it is because of the change in the speed. So the major one is the change in the wavelength. So the change in the wavelength, as light moves from one medium to another, will cause the change in the speed of light. So those are the two things. Whenever they ask what are the causes of refraction, changes in the wavelength, changes in the speed of light, as light moves from one medium to another of different optical densities. Okay, I think we can now continue. Now, we have what we call common terms used in the refraction of light. Now, when we talk about the common terms, we are looking at when we are defining refraction, what are some of those terms that we use? And some of the terms we use, we have this ray. Allow me, I'm going to label it like this. This one can be my A, this one can be my O, and I can have B here. Now, this angle here, this is what we call the normal line. Now, the angle, this ray, this is what we call the incident ray. This ray here from A to O is what we call the incident ray. This line here is what we call the normal line. Then from O to B, here is what we call the refracted ray. Refracted ray. And then So those are some of the things you need to know. The incident ray, the refracted ray. Then I, whenever you find I stands for the angle of incidence. Angle of incidence. Then when you find R always will stand for the angle of refraction. The angle of refraction. Now, what is important? Now you need to know, because sometimes they can even trick you and they say, what do you mean by the angle of incidence? So the angle of incidence is that angle between the incident ray and then the normal line.
In progress. Correct. So we can all agree that water is a compound while air is a mixture.
So the angle between this incident ray and the normal line is what we call the angle of incidence. And then the angle between the normal and the refracted ray is what we call the angle of refraction. So that one you must be well conversant with those ones. But that one is just for your own understanding. In case maybe they ask you, you need to know. And maybe in case you're making some explanation somewhere, you need to know. So I've said that. Yes? Okay. Okay. So that is briefly about it. So these are the different definitions of those things that I've been talking about. Now, we have what we call the laws of refraction. But as we look at the laws of refraction, can we first tell me, what did you learn about laws of refraction? What were they? What are the laws of refraction? Anyone who remembers? Yes, tell us. Daphne? Daphne?
The incident ray,
Mm.
the incident ray, reflected ray, and the normal at the point of incidence all lie in the same plane.
Okay, very good. Can you now convert for us that law to refraction law? I want you to remove the word
Have
refraction.
you gotten me?
Yes, you are correct. Yes, I wanted you, Daphne, to change for us now that law from refraction law to refraction law.
Pardon?
I want you to give us now the refraction, that law you have stated. Eh?
The incident.
Uh-huh. Continue.
Nothing, go on.
Let me mute you. It seems some people don't want to mute. Okay. Now, what Daphne told us was the law of refraction. Okay, I think let me disable some features now. Okay. Now, what Daphne told us was the law of refraction. Now, when it comes to refraction, now we state the same law, but what changes is that when it comes to refraction, we use refracted. Many candidates always make a mistake. They say the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. But which mistake do they usually do? For them, when they reach here, instead of using the word refraction, they write refraction. So please, always, this is what makes the candidates fail. This word only they miss out on this word and things become wrong. So you need to know that when it comes to refraction, stick to the word refracted ray. Then the second law tells us that the ratio of the sine of angle of incidence, and I want to be very clear, the word ratio is very key. When we say ratio, ratio comes from ratione, and ratio means a fraction. It means a fraction. So, meaning that here we are going to look at the fraction of the angle of incidence and the angle of refraction. So, when we talk about sine of angle of incidence, so we shall have sine I to sine R. And you know that when I'm talking about ratio, always we have the word 2. So, the ratio 2. So, meaning that this is our sine of I, and this one is our sine of R. And now you need to be very clear that is always equal to a constant for a given pair of medium, meaning that this one is equal to a constant. Now, in I think O level, they used to tell you that for you can just write this and then say sine I is equal to this, sine R is equal to this. But at this level, we expect you to say the law in words, that the ratio of the sine of the angle of incidence to the sine of angle of refraction is constant for any given pair of medium. So that one should be able to stick into your head as such that you can be able to do. And now this law is what we call the Snell's law. So this is like in physics, when you discover something, it is named after your name. In case you are Daphne, they can say Daphne's law. In case maybe you are Alvin, they say Alvin's law. Bashir, they say Bashir's law. So it depends on who discovered it. So it's what we call the Snell's law. And this thing that we are saying, the constant means something that does not change, is what we call the refractive index. We call it the refractive index. So let me allow it first. Yes, Daphne.
Excuse me, sir.
Yes.
They ask you for laws of refraction, cut the second law. You write that very law, and then when they tell you state Snell's law, it's still the same. Yes?
Teacher, let me answer her.
So, I beg your pardon, Daphne.
When they tell you state Snell's law, are you supposed to write that second law of refraction?
Yes, exactly.
And then
Only.
when they state the laws of refraction, it still coordinates there.
Yes, you write 2. When they say laws of refraction, you write both of them. When they ask you Snell's law, you write only the second law.
Okay, thank you.
Okay. Okay. So we are going to, yes. And even here, I may wish you that even here, you can even make it better and say the normal line. Yes, you can say the normal line. Okay. Someone, Asap ask.
Good afternoon, class.
Good afternoon.
Yeah, teacher, like we have this sheet of like that word in. We always, some people use on. What is the difference between on and in?
On, eh? Now the best, like, let me say this is let me say this is water. When I put when something goes inside, let me say I have a piece of paper. When I put a piece of paper on water here, it will first float. So I'll say it is on water. When it absorbs the water, it will sink. So I'll say it is in water. So in, it means inside. Then on, it means it is on that plane. Now, the best word can be on. But now when it comes to refraction, refraction stick to the word on. Because when it comes to refraction, light doesn't go in. But when it comes to refraction, light goes in. So for refraction, light will come, it will get incident, and then it will get reflected. So it is on the surface. It is on the same plane. But when it comes to refraction, light goes through. So that's why we are using the word in the same plane. I don't know whether you have got the difference. Have you got a difference? As soon you can accept something. Okay, let me hope so. Okay, yes, good. Then Innocent, unmute. Innocent, unmute. Innocent, unmute. Oh, okay. Innocent is unable to unmute. Infinix, unmute.
Master,
Yes.
here I'm saying that they are saying Snell's law, you remove the word constant and it's called refractive index. Am I clear, sir?
Pardon?
Here I'm seeing this is called Snell's law, and this constant is called refractive index.
You are saying?
Snell's law states that according to what I'm seeing here, Master, they are saying that this constant is called refractive index. What you
Yes.
mean in the second law of refraction, I remove the word constant and I replace it with refractive index.
Now, why we don't want to commit to the word refractive index is because different mediums have different refractive index.
Yes.
So take an example. When you say refractive index, take an example for air is 1. So when for you say refractive index, someone may think that you have mentioned maybe, let me say you have put the word refractive index. When you put for air, which is 1, the statement does not make sense. So that's why we say is equal to a constant for any given pair of medium. And here, when we are placing in the medium, remember we said that refraction, we compare two mediums. So we compare either air, water, water, glass, like that. So that's why we always say, let it be to a constant, because you are not sure of which medium it is. And when even we shall look at the definition, when you are defining what refractive index of a medium is, it differs. So here the best word to use is just a constant. Constant means that it does not change. But the moment you put the refractive, it doesn't change for any two pairs that of the medium that are the same. Hope that is okay. Okay, so we are going to continue. Now from here, like we have said, that whenever I have my n is what we call, so Snell's law is given by this. This is what we call Snell's law, that the refractive index is sine I out of sine R. Now, when you look at our question, they are telling us that we have a ray of light incident in air. Like you have, this is your light. And light, when it comes, it is incident like this. The angle you have here is 30 degrees. So find the value of the angle of refraction if the refractive index is 1.5. What does it mean? That light is entering into a medium that you are not sure of. But they are telling you the refractive index of this medium is 1.5. So what are we going to do? We just substitute because we want to find out this angle of refraction. So our n is the refractive index. So whenever you find n in physics, we'll be representing the refractive index. So I will say 1.5 is equal to sine I, which is 30 out of sine of R. Then I'm going to ask myself, you can do your physics, cross multiply 1.5 sine R is equal to sine 30. Then after you divide by 1.5, divide by 1.5, sine of R will equal to I don't know what you get when you place your calculators. But me, I'm getting 0.333. And when I get the sine inverse of 0.33333, I'm ending up with an answer as 19.7 degrees. So that is my angle of refraction. But now what do I want you to notice? That light was coming from air whose refractive index is 1. And light is entering into a medium whose refractive index is 1.5. We know that 1.5 is a refractive index of glass. That one, at least you should be knowing. Meaning that air is a less dense medium and glass is a more dense what? More dense medium. So the angle of incidence must always be bigger than the angle of diffraction. So that's why we have 19.47. If you ever get an answer, let me say the answer you have gotten is 40. It means you are wrong. Anything above 30, it will imply that what you are doing is wrong. Because when light is moving from a less dense medium to a more dense medium, we expect that now the angle of refraction is going to be very small because its wavelength, its speed, all of them have reduced. Members, are we together? Let me know whether we can continue in the chat or whether you have any questions. I'm seeing a hand up. Sap, you can unmute in case there's a question. Okay, I think Chiberu Peter, you can unmute.
Yeah, Master, I'm requesting for your pardon on the last part of the explanation.
Of this number?
Yes.
Okay, where exactly?
You talked about something being less. We expect something to be less something.
I beg your pardon?
Yeah, on the last part, like of your explanation, you talked about if we expect something to be less.
Yes, like I'm saying, like when you are let me say, when you move from air and you jump into the swimming pool, do you notice that your energy levels goes low? Do you notice that your speed will always be low?
Yes.
Yes. Now, with that one, that's what I'm saying also for the angle. That in air, you will jump very quick, you will jump very far. But when you enter into water, you can't. So whenever light is moving, when you are moving from a less to a denser, the angle always changes. The angle becomes small because your speed, your energy, everything has gone down. But when you are moving from water and you are going into air, the angle will always increase, will be bigger than what you had. Hope I'm okay, Chiberu, on that.
Yes, thank you.
Okay. Okay, we are going to proceed. Now, we are going to proceed to what we call refractive index. Another term we are going to look at is what we call absolute refractive index of a medium. Now, when we are looking at refractive index, like the way we have seen from Snell's law, that we are looking at the sine I out of sine of R. So by definition, when we are looking at sine I, sine R, and we are defining what refractive index is, in simple terms, refractive index means the ratio of the sine of angle of incidence, the sine of angle of refraction, when light is moving from air to any other medium. And to be very, very specific, when we define refractive index, we're defining what we call absolute refractive index. When we define absolute means total. That's I think the simple English word, total refractive index. It means that our medium where light is coming from is air and is entering into any other medium. So that's what we call refractive index. So refractive index, we are looking at how sign of the incidence angle and the sign of the angle of refraction vary. So when they ask what is refractive index, what is the absolute refractive index, then it means that our light is going to be moving from air and it's going to be going into another medium. But here, do not specify another medium. Don't say from air to glass. No, there is no need for you to specify. But we have said that refraction, we can as well define it in terms of speed. So you can easily say is the ratio of the speed of light in vacuum to the speed of light in another medium. So here, please, you need to be very specific. And the common word you are going to be finding, they will ask you, what is absolute refractive index? Please do not get confused. It's not a new word. It just means that you are moving from air and you are going to another medium. But here you specify the medium where you are coming from, that you are moving from air and you are going to another medium. Hope that is okay. Okay. Now, yes, Daphne.
Excuse me, sir. If they ask you, maybe define absolute refractive index. Is it the same as define refractive index of a material?
Yes, they are the same things.
Oh, okay.
Okay. Okay, now, when a ray of light is traveling from air to glass, then the refractive index is written as, now for such a case, I write N, I will say air to glass. When you find such, it means light is moving from air to glass. If it is traveling from glass to water, the first letter represents the medium where light is coming from. The second letter represents the medium where our light is going. So when it comes to that second medium, now for this case, I will say it is coming from glass to water. So I write glass refractive index of water. And please take note, glass refractive index of water is not the same as water refractive index glass. These are totally.
Please unmute and say something.
So these are totally two different things. So please do not confuse, they are not the same. Here it means light is moving from glass to water. Here it means water to glass. And when you make your calculation, still your calculations would be different. Hope that is very, very fine. So please do not. So the first letter represents the medium where light is coming from. The second letter represents where light is going or where light is heading to. Okay. Yes, Collins, we are going to come to that formula. Okay, I think we can proceed. Yes. Now here, they ask define. Now here is where I want you to pay attention, Daphne. When they ask define refractive index of the material of glass, here they have specified the medium. Because we have said that refractive index of a material means that we are moving from air or vacuum. But since here they have told us of glass, then we shall say to glass. So here, if you mention to another medium, then you will not be marked right. So please pay attention to it. That when they say the material of a glass, it means you must specify where light is coming. So light is coming from air and is entering into glass. So you must say from air to glass. That's what you call refractive index. Hope that is very fine. You can as well find such a question that what does it mean to say that refractive index of water is 1.3? So please make sure. So let me first allow give you some 2 minutes to summarize those 2 points. I know you might not have met them somewhere, but let's summarize them. Summarize them somewhere for your revision. So let's summarize them. These are questions where they will put for you 2 marks, and you may start losing your 100 with you not knowing some of those 2 things. So summarize. When you finish, you let me in the chat that okay, I think people have finished. Okay, we can proceed. Okay, then we have another law we call the principle of reversibility of light. Now, this is an important principle that at times even it can act on our lives. There are some things that we do in life that cannot be reversed, but there are some things you do that can be reversed. Things that cannot be reversed in life, I think the only thing I know that has ever been done, I think it was last done by Jesus or Muhammad, is whereby someone died and he came back. But death is non-reversible. You cannot reverse it. Once someone dies, he has died. He cannot come back to this real life. But there are some things that we do that at least can be reversed. Now, the same thing happens to light. That when light is moving, when light takes a given direction, or when you move from Kampala to Jinja, you can use the same route from Jinja to Kampala. That's what we call reversibility. So us moving, when you go from home to school, you can easily come back using the same route from school to home. That's what we call reversibility. So reversibility means that when light moves from one medium to another, it can actually follow that same path and it goes back where it came from. So that's what we call the principle of reversibility. So principle of reversibility, it means that the path that light takes is reversible. It means that light can take exactly that same path it used as it was moving from one medium to another. So when they ask you, at times they may ask you, explain the principle of reversibility. When you see the word explain, here accompany your explanation with a drawing. When they just tell you, state the principle of reversibility, just state it that the principle of reversibility states that the path taken by light is reversible. That is to say, if a ray of light is reversed, light will follow exactly the same path. But if they ask you to explain, please accompany it with a right diagram and now show both the diagrams. You cannot say that light is moving from medium 1 to medium 2, show when it is going, and then show when light is following the same path. That's what we call the principle of reversibility of light. This principle can also be done when it comes to practicals. It can be done in practicals. So when you can carry out an experiment and you show it. It can be done in the laboratory. And the same thing happens when it comes to Snell's law. It can also be performed in the laboratory. Those who were doing light at O level, the glass block you were doing, that was Snell's law. You are trying to prove Snell's law. That was O level. Yes. Okay. This is what you call the principle, that light will always follow the same path. Okay. Now we are going to look at the relationship between what you call refractive indices. Now, when it comes to relation between the refractive indices, we are going to ask ourselves, because I know you have seen these things and some of you have just gone on to cram. But I want to warn you that when you reach a level, please minimize the cram work, because it will really affect you in the future. A cram work is bad. Always embrace understanding from the first principles. The moment you understand from the first principles, you'll find yourself remembering those concepts without a lot of putting in a lot of efforts. Now, this is what I want us to learn how to derive. When I have, this is my ray of light, this is my glass, and this is air. So we are considering a ray of light that is moving from glass to air. So we know very well that this is what we call moving from glass. We say that glass is a denser medium. So meaning that light, when it's moving into a less dense medium, here we expect it to move away from the normal. So also when you are drawing, put in that common sense that if this is angle X, here, this angle must be bigger than this one. So this one, let me call it Y. So my light will move like that. And when we are doing light experiments or light drawings, arrows are very important. Why? Because those arrows are the ones that show us the direction that light travels. We say that the arrows are very important. So we know very well from Snell's law, from Snell's law, and some of you, at times, you are not very careful. When you are writing, some of you may end up writing this. This one is not Snell's law. This one in English, it means many, yet the law is one. So you need to be very careful always to put that apostrophe to show that it is one law. So we say that here our light is moving from glass to air. So we have said that one, we denote it as glass refractive index of air is equal to our sine, light, the angle of instance is X, I will say sine X out of sine of Y. Hope that is very okay. That is Snell's law. So this is my first equation. Now, by the principle of reversibility, you know that principle that we have just talked about. By the principle of reversibility of light. Initially, our light was moving from A, it went to O, and it went to B. But by principle of reversibility, our light can follow another path. If a ray, let me say BO, is reversed, when we reverse, it is refracted, it's going to be refracted at the interface along or to A. So when we reverse it, it means we are going to have a diagram of this nature. We shall have this one being reversed, this one will be Y, and we shall come here and it will be X. Now, by reversing, it means that now for this time round, our angle of instance is going to be air, and then here we shall enter into glass. So how do we write it? We shall say refractive index is coming from air to glass, which will be sine of Y out of sine of X. So now this is my second equation. Now, when you look at these two equations, you are noticing something similar. And what are you noticing? You are noticing that one of them is a reciprocal of the other. Here we have sine y out of sine x. Here we have x sine x out of sine y. Meaning that when here I say 1 out of air glass, it's the same as sine of x out of sine of y. But now here, so you have noticed when I say 1 out of, I'm going to come here and I take the reciprocal of that 2. So what are you noticing? You are noticing that now my equation 3 is related to equation 1. So, and this is what I want to conclude, that glass refractive index of air is the same as 1 out of air refractive index of glass. And now this is an important derivation. They can ask you to derive it. And how can they pose the question? They can say that, show that the refractive index of a ray of light traveling from glass to air is equal to the reciprocal of the absolute refractive index of glass and air. So they can ask you the question of that nature. That show that the refractive index of a ray of light traveling from glass to air is equal to the reciprocal of the absolute refractive index of glass and air. So this is what they want you to derive. Kindly write. In case you have any question, ask. In case there is any question, ask. Alert me in the chat whether we have understood. Peter Chiberu. Okay, Peter Chiberu. Okay, Abdu, ask. Yes, Abdu, ask.
Master, I beg of your pardon, please.
Okay. From which point?
From the second equation, yes.
From here?
Yes.
Okay. Now, when you look at this, you are noticing that for the second, we are applying the reversibility. We say that reversible means that light can take exactly the same path it used. Like, you know very well, when you are going home or when you are going from home, you can say, I'm from home to school. You have seen those disciplined children. They use the same route even without diverting. That is how light behaves. That when light is moving from air to glass, that one we shall say air refractive index of glass. But by Snell's law, always we know that here, when it is coming back, the angle here is y. So I'll say sine of y. Out of, it is entering into glass. Into glass, I'll say sine of x. Now, when you look at this equation and this equation, they are mathematically related. What does it mean? You know that air refractive index of glass is like there is a K1 here. So it means that air, no, let me use this, that I have 2 is equal to x out of y. Mathematically, you can do your cross multiplication. But you know that this 2 is like out of 1. So you say 1 times x, 2 times y. So this is like 2y is equal to x. So when you divide here by 2, here you divide by 2. It is almost the same thing here. But in math still, also you need to remember that when I have 3 out of 2 is equal to x out of y, when I put this up and I put this down, I do the same thing this side of the equal sign. I put this up, I put this down. So it means 2 out of 3 is equal to y out of x. Mathematically, this equation and this equation are the same. As long as in everything, what you have done on your left and right is the same thing you have applied to the original one. Still here is like this is a refractive index of glass out of 1. So I can take this one up, I take this one down. But what I've done on my left, I did on the right. I take this up, I take this down. So I'll have 1 out of air, refractive index of glass, is equal to sine of x out of sine of y. But when I look at the first equation, already I have sine x out of sine y. So where did sine x out of sine y? I'm going to substitute this. So I will just come here and I substitute here as 1 out of air, refractive index of glass. So whenever you have those mediums, like I told you earlier on, that glass refractive index air is not the same as air refractive index glass. I told this is not the same. But for it to be the same, it means glass refractive index of air is the same as 1 out of your medium, which is air refractive index of glass. Let me hope we're on the same page now. Are we on the same page? Not yet. You can let me know through the, okay. I think we're on the same page, yes. So I can read this question again, just for you to for you to have it at the back of your head. They can ask you that, show that the refractive index of a ray of light traveling from glass to air is equal to the reciprocal of the absolute refractive index of glass and air. Always highlight the keywords and then go on to work it out. Okay. We have another one. So we have started the derivation of some of the common things we are going to be finding in our topic of refraction. Now, when you look at my screen, it is showing rays of light that are traveling from one medium to another. Now, from the definition of Snell's law, we say that it should be is constant for a given pair of medium. When you look at ours here, our light here is coming from air. So from air here, we can call it IA. It's entering into a medium which we don't know, which we are calling I1. And it is getting out of I of A. And here is I of 2. What do you need to know? That this angle here and this angle here, they are the same angles. Why? These two angles are alternating angles. Angle I2, which is the refraction angle, is equal to this angle. Why? Because those two angles are still alternating. Now, when I'm applying the Snell's law, here I'm going to say, applying Snell's law. Applying Snell's law at air medium 1 interface. So we know that from Snell's law, always from Snell's law, our light is moving from air and is going into medium 1. So I'm going to say, here I can say air and my light is entering into medium 1. It will equal to sine of I of air, because that's why it is coming out of sine of I of medium 1. If you don't use this approach, then I want you to go on and say, no, I don't want to use this approach. Which approach can I use? Now, the second approach you can use, you can say that this is air. My light is coming from air, sine of the angle of air, and is entering into into medium 1, which I don't know. I say refractive index of medium 1, and then sine of I1. Now, this is my first equation. Then after the first equation, I know very well that refractive index of air is always 1. So I will say 1 sine I of A is equal to N1 sine of I1, meaning that sine IA is equal to N1 sine I1. This is going to be now my equation 2. Now, afterwards, I'm going to come to the second medium, which is medium 2 and the air. What am I going to say? Applying Snell's law at medium to air interface. Because you are noticing our light is coming from medium 2 and it's going out of air. Why have I went to this medium? All these are mediums. But since the first one has a relation with air and the last one has a relation with air, that's why I've gone in for the last one. So our light, I'm going to say refractive index N2, which represents, so for this medium, it is N2, this is N1, this is N air, and also here is N air. N2 sine of I2 is equal to N air sine of I of air. So here we shall have N2 sine of I2 is equal, N air is 1. So meaning we shall have sine I of A. And this one, I'm going to call it my equation 3. When you look at our equation, you are noticing that sine IA is the same as N1 sine I1, and we have it here. So I'm going to just come and I say N2 sine I2 is equal to N1 sine of I1. I've substituted. Sine IA here is the same sine IA here. So it will be equal to this. And therefore, I can conclude that N1 sine of I1 is the same as N2 sine of I2. That even if I have 3 mediums, it will be N3 sine I of 3. So you are noticing that it is the same thing. And that's why now we're saying that N sine I is always equal to a constant. Because for it does not. Are we together on that, friends?
No.
From where?
Applying Snell's law on the second medium.
Second medium, Now, when you look at the second medium, our light is coming from N2 and is going into air. Here the angle is I2, and here in air, the angle is IA. So I will say N2 sine I2. Whatever it is in this medium where light is coming should equal to the refractive index, which is of air, then sine of IA. But N of air is 1. So I say 1 times sine of I of A, which is the same as sine of I of A, is equal to N2 sine of I2. But initially, you had got the here from equation, you know very well that sine of IA is the same as N1 sine I1. So you equate. Is that fine? Not yet?
Yes.
It is okay.
It's fine, sir.
Okay. It is fine? Okay.
Yes, sir, it's fine.
Yes. So they can ask you to derive it to show that n sine I is equal to a constant. Now, whenever they tell you that derive, show, do this and this, please make sure you define the variables, the terms you are using. You can say that consider array, have those opening statements. Don't just come out of the blue and bring your things without defining them. Say, consider array of light traveling from air through a series of medium 1, 2 of refractive index N1 and N2, and finally it merges into air. So make sure you have opening statements that define the variables you are using. Okay, should we continue to another screen? Or people are still writing? Are you writing or we continue? Okay, we continue. Okay, now we are going to do some few calculations. The first one, they're asking us that calculate the refractive index of glass if a ray of light is incident onto it at an angle of 60 degrees and it is refracted at an angle of 30. Now, I always advise that we don't need to cram, but you must understand. Come up with a sketch. I'll come up with my sketch where I have a ray of light. It is incident at 60 degrees. So this is my 60 degrees. And is refracted at 30. So that one, even when you're drawing, make sure you do reasonable sketches. So this is 35.3. When you look at it, you are noticing that light is moving from a less dense medium and is going into a medium that is denser. 2, when they tell you that refractive index of glass, what has to come into your mind? That one, we know that refractive index, it will mean that light is moving from air and is going into another medium, which is glass. So I expect you to say that N sine of I is equal to a constant. So here we shall have our air, and this is the glass material where light is entering. So I'll expect to say N air sine of I of A is equal to N of glass sine of I of glass. So N air is 1, sine of angle, which is 60, is equal to N glass, which you are looking for, sine of 35.3. So this will be sine 60 is equal to N G sine of 35.3. So divide by sine 35.3, divide by sine 35.3. This and this will cancel. So have refractive index is equal to, so when you place your calculator, sine 60 divide by sine of 35.3, you will notice that your answer is about 1.498. So here I'm getting 1.49868. So I can conclude that refractive index is approximately 1.5. Members, are we together on that?
Master.
Yes.
There's no units on our answer.
Yes, there are no units,
Okay,
because sine I is angle. Angle out of angle is nothing. Okay. Okay. I think Chiberu, a question?
Yes, teacher. I wanted to know about this statement of refractive index
I do
of
that.
Continue.
I don't want to be disturbed. So
why you're putting glass, like why isn't light traveling from glass to air? You're putting air first, then glass second.
No, light can travel from both. It is okay. But here, since they told us it is incident, onto the glass material, that's why we started with air to glass. But it can as well be light is moving from glass to air. Sure, I don't know that it is fine.
Master, what I want to know is that they said incident, like I'm not understanding that statement. Like
Incident means falling. Falling. Imagine you move out from the tree and you fall down. So you are going to fall onto land. When you move from somewhere and you fall into swimming pool, you are moving from air to swimming pool. So that's what you call incidence.
Okay, sir.
Is it clear now?
Yes.
Yes, so here they're like telling us that light is falling from air onto this material from somewhere. Okay. Okay. Now, can we first try for me this, everyone? Try and you put your answer in the chat. Looking through the chart. Yes. Now, Bashir's daughter always avoid writing to 0 decimal place in physics. Whenever you get your answer, write 2. If there are 2, write to 2. 3, write to 3. But never write to 1 decimal place. Okay, yes. So that is the answer. Thank you. Yes, I'm saying people are getting the answer.
Progress. Okay, I think I've answered. Okay, can I ask my question? Okay. You were like, we shouldn't outline our quotes in the rough. Yes.
Okay. Okay, good. Now let us try another number. We are trying that number. Let everyone first try. Yes, here you can notice that they have given you the speed. Now, one thing I want you to take or to pay attention to, we say that refractive index, we can as well define it in terms of speed. So we say that refractive index is the speed of light in vacuum to speed of light in a given medium. So I think that is what now here you need to apply. That refractive index can be the speed of light in vacuum to speed of light in a given what? Speed of light in given medium. So in vacuum or in air, we use C. Whenever you find the C, it means speed of light in vacuum. Then out of speed of light in any given medium is where you can use V. Now, for such a case, our light was moving from the liquid sine of the angle of instance of the liquid into entering glass sine of R. Now, for this case here, where we have L, refractive index, we are going to substitute with C out of V. Because here we have the speed of light in the given mediums. So that is now what you need to do when it comes to such numbers where they have given you in terms of speed. So, so that is what you have to do. So here I will say NL, that is for the liquid. I will say C out of the velocity of light in the liquid, sine of I. But sine of I is 60 is equal to Ng, which is C out of V of glass, sine of R. Now, simple math, here when I do the mathematics, C and C are common. I can easily cancel them out. So I remain with the sine of 60 out of VL is equal to sine of R out of VG. But you can notice that you have VG, you have VL. So I can say sine of 60 out of velocity or speed of light in the liquid is 2.4 exponent 8. So I say times 10 power 8 is equal to sine of R out of the speed of light, which is 1.2 exponent 8. Then I'm going to go on and cross multiply. So I'll have 1.92 times 10 power 8 out of 2.4 exponent 8 is equal to sine R. Here I have sine of 60. So do your mathematics, and come up with the answer and share with us in the chat the answer you have been able to get. Yes, I'm going to wait in the chat the answer you're coming up with. Okay, I'm seeing the answers. Yes, that is very okay. 43.85. Thank you, degrees. Okay. Yeah, I'm seeing everyone has gotten Christabel, Stewart, Benon, Bashir's daughter, Arwood, Aitawa. Good. Okay, so that's how you relate whenever they give you in terms of speed. Okay, I have another one. First write this one and then we try it out. You draw and write it. Okay, let me hope you have. Yes. Now we are going to try it together. Yes, but I know some of you might be giving it a try, which is okay. Which is okay. First give it a try. First give it a try. You never know. We're on track. And I don't want to limit your creativity. Give it a try. Yes. Yes, give it a try. Okay. Hope my screen is back. Is my screen on? Okay. Members, are you trying? Okay. Bashir's daughter. Okay. Now, they're telling us that the diagram shows a slab of glass of uniform thickness lying horizontally. Above is a layer of water, and the ray of above is a layer of water, and the ray of light is instant to the arrangement from downwards and is reflected successively at points ABC as shown. Calculate angles X, Y, and Z. Now I'm going to ask you, can we first calculate angle X? Light is moving from air to glass. First calculate X. And members, that's what I'm going to first ask you to do. Let everyone first calculate angle X. When you get your answer, put it in the chat such that we can know what you have. In the chat, 35.26, that is from Stewart. Okay, thank Okay, 35.26, Christabel. Okay, that is good. Okay. I think people are getting there. Bashir's daughter, Christabel Stewart. Good. Now, I expect you for the first one, for this first layer we have, to tell us that you are moving from air, sine of 60 is equal to n glass, sine of x. Our air is 1, sine of 60 is equal to n glass, which is 1.5, sine of x. What is going to happen is that I'll have sine of 60 is equal to 1.5 sine of x. So you divide by 1.5, divide by 1.5. So I'll have my sine of x is equal to, now here I want you to pay attention, avoid rounding, doing things on the calculator. So here I expect you to first write for us 0.5735. And then after you say x is equal to sine inverse of 0.57735. So according to what I have here, I'm getting your answer as 35 point. Think in the chat members, we are getting 2626. Okay, 26 degrees. Now, after obtaining your x, you're going to notice that x and the angle you have here are alternating angles, meaning that here you have 35.26. So you're going to use this boundary of glass and water to find y. So let's find y. Okay, I'm seeing some answers coming into the chat. 40.63, Peter, Bashir's daughter, Christabel. Okay, 40.63. I want to say the answer is correct. The answer is correct. The answer is correct. After obtaining that one, I want you to go on and find your Z. And what is your Z? Yes. Z is also 40.62 according to Christabel. And now for search, you must also tell us the reason what you are basing on to say 40.6. And always look at the marks allocated to the number. If at all you see 5 marks, then you may not need to just make a conclusion, but you must go on and show how you can get it. But I'm happy people are getting it. So your Y is 40.7. Your Z is also 40.7. Reason, those are alternating angles. Those are very good, Christabel. Those are alternating angles. Okay, hope we're on the same page. Because they're alternating angles. Because they're alternating angles. Okay. Because they are alternating angles. Okay. Have you covered the trigonometry? Have you covered trigonometry? Kindly let me know in the chat whether you have covered the trigonometry. In case you have, just tell me yes or no in the chat. Because there's a number I want us to try out, but it requires to have the knowledge of trigonometry. So I want to find out whether we have, okay, good. If we have covered trigonometry, allow me to give you that number and we try it out. Okay. Let me share it and we try it out. Okay, that is the number. For this one, okay. Yes, for this one, you are going to write it. Okay, sorry. This one, I want you to write it in a very good way. It is NT sec theta out of C. Like that. First write, and then we can try it together. Okay. Now, when they give you a number that involves you to calculate, like after, it is always a good practice. It's always a good practice for you to first make a simple sketch of a drawing. Now, they're telling us that a monochromatic light, when they talk about mono, it comes from the word monocotyledonous. Mono means one. It means one light. It means light of one wavelength. That's the meaning of the word monochromatic light, because you know that light is composed of different colors. So meaning that if you don't use monochromatic light, it means that different colors can be dispersed. So in order for us to obtain one color, we always use monochromatic light. It's incident onto a block of material placed in a vacuum. Now I have, this is vacuum, we said is like the air. So this is our block of material that is in air. And we have light that is incident. This is our source of light that is incident onto that block, meaning that when it comes here, this light will enter into the glass. Is refracted through an angle theta. So the angle of refraction here is theta. That is the angle of refraction. If the block has a refractive index n, this block here has a refractive index n, and thickness, this is what we call the thickness, and that thickness is T. Hope we are together on that. Then they're asking, so this is our angle of incidence, I. So we are moving from air, because they told us it was in a vacuum, and we are entering into glass. So they're asking us to show that the light, that light takes T to emerge. Emerging means that light moving out. So it means that for light to get out at this point here, which I can call B, here, they're telling us that show that this is the time it takes. So imagine this is my O, this is my A, O, and B. Now, in order for me to be able to calculate, what do I need to know? One, I need to know, okay, a minute, I think you're here. Okay, so it means that now we are going to ask ourselves, they want us to find the time. But how can we relate time? So like you have told me, you have covered your trigonometry very well. I want to extract, they want the time it merges from O to where you have B. And the angle here we have theta, here is the thickness T. Now what do I have? I have here, let me put here 1 and I have 2. Basing on this angle, which trigonometric ratio relates this and this? Type in the chat, which trigonometric ratio relates those two sides? I want to just check whether people have an idea. 1 and 2 for that triangle of ours. Okay, someone is saying sine, cos. Yes, okay, some are saying cos and sine. Okay, now we shall go back to our SOHCAHTOA. Now, where the angle faces is what we call the opposite. Longest side is the hypotenuse, and this is the adjacent. Looking at the question, we have the adjacent 1 and hypotenuse, which is 2. So meaning the best one to use is the cos. So now I will say that cos of theta is equal to adjacent, which is T, out of hypotenuse, which is the distance O to B. And therefore it means that our O to B is the same as having T out of cos of theta. But still from trigonometry, we know that when you look at our answer, they have a sec, meaning we are going to look out for the sec. We know that from trigonometry, sec is the same as 1 out of cos theta. So when I come here, I will say that my OB is the same as 1 out of cos theta times T. So, but 1 out of cos is the sec. So meaning that I will say my O to B is the same as T sec of theta. Members, are we together up to that point? Yes, because we don't want to leave anyone. Is that point clear? Okay, yes. Okay, Abdullah is saying yes. Bashir's daughter is saying yes, yes. Okay, now we continue. But we are looking for time. So we know very well that always our distance is always given by speed times the time. So distance, the light is going to move is O to B. That is the distance. Speed, I can denote it by V. And then the time, I'll denote it by T. So what does it mean? It means that now, in order for us to obtain our, so this is very important. We know our OB is the same as T sec theta. We have our speed, which is V, and we have our T. So that one, but this is time, this is thickness. So do not confuse them. Allow me to use capital T here. In fact, not to confuse, this is capital T. So in order for us to, so this is very important. So OB is T sec theta is equal to VT. Now, our V is the same to T, or I can do anything. I can say that our time T is given by T sec theta out of V. But still I know that our speed of light, we know very well that refractive index is the same as of the speed of light in vacuum out of the speed of light in vacuum in a given medium. So for this case, speed of light when light was in air to the speed of light when it was in glass. So meaning that V is the same as having, when you do your cross multiplication here, I'll have N V is equal to C. So my V is the same as C out of N. So where there is V, I'll put C out of N. So I'll say my time is going to be T sec theta out of C out of N. And mathematically, this one, you can write it as T is equal to NT sec theta out of C. Remember here, I've jumped that step, T sec theta divided by C out of N, which is the same as T sec theta times N out of C. So which will give us NT sec theta out of C. So that is how they want. But here, do not forget, always define that where let capital T be the time taken by the particle to move from O to B. Okay. Hope that is okay. Any questions? Is that fine? Any questions? In case you have any question, you can raise up your hand and ask. In case you have any question, you can raise up your hand and ask. Okay, yes, Peter.
Master, I want to know when we are dividing, teacher, like for example, you said that time T is equal to T sec theta divided by C over N. Sometimes I see, like, I don't know, should I say mathematically, when they are just multiplying, like that fraction is multiplied with a C, like that N is multiplied with a C. But here I'm seeing it going up.
Oh, no. Now, when the N is multiplied with a C. Peter,
Yes.
now that one, I actually have not yet seen it somewhere. Yes. But now for you, what you have to know, for you now, what you need to learn is to know that always N is given by C out of V. So there is no any way where you will have N times C. They cannot divide. They cannot multiply each other.
Okay, sir.
Okay. 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 Okay, I think according to the chart, I think we are very fine. So we are going to end at this point. We are going to end. We are not going to go any further. We are going to end here.